Hey guys, um, coming to you again tonight. Don't mind the screaming or the screeching outside. It's just somebody getting murdered. Probably fine. Um, that being said, welcome to Video ECE 46 again. So today I'm going to talk about the notion of a state transition matrices. Um, These are essentially a way to describe the evolution of your system through a matrix dependent on time. So as we saw, similar to like what we saw with Laplace transforms. So if we recall, let's pull this up. So if we recall, for an LTI system, the solution to the state equations can be found using a Laplace transform approach, which you may have seen in your differential equations class or other maybe signal processing classes or something like that. But through this Laplace transform, which I denote as this calligraph L. So L of x dot is equal to the Laplacian of ax plus bu, which implies that, so this Laplacian of, this Laplacian of x dot is, oh, I got a new dog. He's down here. He's roaming around as well. Do you want to say hi? Come here, Jack. Come here, Jack. Oh, here's my new pup. His name's Jack. He's pretty cool. He's sleepy though, because it's 11. Okay. Thanks, Jack. I hope you made my class proud. Okay, so the Laplacian of the derivative of x is equal to s times x of s minus x naught, where x naught is the initial condition. This will be equal to a x of s plus bu of s, which implies that the solution x of s is equal to s times a times I minus a. Oops. Inverted times x naught plus bu of s. Okay, so now in this case, if there is no forcing function, so no control input, then we could say that x of s is equal to, so basically if we look back at this equation, if there's no forcing function u of s, then this part goes away. So this goes away there. And then we get s times the identity minus a inverse times the initial condition of x. Okay, so now if we take the inverse Laplace transform of this, so let's take the Laplace transform inverse of x of x, s of s, this will give us back x of t, and then we look at the Laplace inverse of this quantity, two parentheses there. There, nope, this is there. Great. So now we call, so this part right here, we're going to recall this. We're going to call it as phi of t and t naught. So it's relative to two quantities, two parameters here. And then this capital phi is what we call the state transition matrix. Or just STM for short. Okay. And so again, this phi is equal to the Laplacian inverse of S minus SI minus A inverted. Okay, and this is only true for linear time invariant systems. For linear time varying systems, the state transition matrix is a little trickier to figure out, but it can be done. And so if we take the STM, oops, take the solution. So note that this guy here is now a Zawa solution, right? So now we have x of t is dependent on this state transition matrix times its initial condition. Okay, so now for any given initial time, initial condition, and time t, we are given a quantity x. Pretty simple, right? So it makes it really, if we can do this, it makes it really easy to compute solutions to our system for any parameter x naught, initial time, and future time. And yeah, I should mention that t here, t is greater than t naught, greater than or equal to. Great. So if we take the solution x of t and we, oops, make that bigger there. Trying to make sure that it fits on the screen. Okay. And we differentiate it. We get that x dot is equal to phi dot t of t and t naught times x naught. Okay. So the derivative of x, the derivative of x is just our initial ax, and this will be equal to phi of t naught. And then now x here, x again is defined through this solution here. So that gives us, bring back my guy here. So this gives us a times phi t naught. And this is equal to the derivative of t naught x naught. X naught. So this implies that the state transition matrix satisfies the differential the differential equation okay, so namely that means that by satisfying the differential equation, we get that, remember, any solution to our differential equation has to satisfy that differential equation, right? So if our solution, if we're saying that phi is our solution, then it has to be that phi satisfies this differential equation. Okay, and this is what we showed through here. So if we take, namely, if we take this part and this part, we get that removing this x naught. So removing this x naught, we get that we satisfy this. This implies that we satisfy the solution to our equation. Okay, so for linear time invariant systems, the solution to this equation is pretty straightforward. Okay. Namely, you can find it through evaluating what we call the exponential matrix t minus t naught. Okay, so the exponential matrix we can use MATLAB one way, and then you can also calculate it by hand. But the exponential matrix satisfies this Taylor series expansion minus t minus t naught over 1 factorial times a plus t minus t naught squared over 2 factorial times a squared plus t minus t naught 3 over 3 factorial a cubed plus L to infinitum. So however, as I mentioned before, for near time varying systems, there's no clean way of finding the straight state transition matrix. So it's most important to note that our state transition matrix is not equal to the exponential of a of t minus, a of t, where a of t is the time varying state matrix. So this is the time varying state matrix. So just as with differential equations, determining the solution to a time varying system is non-trivial. There's some more properties for state transition matrix that I'll just list out. I won't ask you to prove one in the homework, but I might ask you to show that one holds in the homework. So some properties of state transition matrices are the following. The first one being an identity property. So namely, if we have the state transition matrix with T naught and T naught, then this is just equal to the identity. This next one is the property of products. So if we have phi of T2 and T1 times phi of T1 and T2, this is equal to phi of T2 and T naught. Okay. This one's pretty easy to show through just taking a sequence of solutions between those intervals. Let's see. The next one is that if we take the inverse of the state transition matrix, say we needed to manipulate it and invert it, it exists, and it's no more than taking the state transition matrix and swapping the inputs, T0 and T1. So they are invertible. Another one that's not in the notes here, that I have here in my book, is that the derivative, as we showed before, just to reiterate, the derivative of T and T naught is equal to a T naught. That A should go away. And then the last one is that the derivative of T naught and T is equal to minus T naught T times A. All right. And that's all I wanted to show you. Next time we'll talk about solutions to the system.